So in this lecture, we're going to introduce electric current. We'll talk a little bit about what batteries do, and then our basic circuit diagrams, how we draw electrical circuits. So to get into electric current, I want to talk about the Van de Graaff machine, the demo I did the other day, and then we'll talk about gravity before, and then fluids in order to build this idea of current. So a Van de Graaff generator, imagine I have this thing hooked up and I turn it on and I build up a whole bunch of charge here. And then I have another conducting sphere that has no charge on it. So we know that there's a big potential difference between these two objects. So, this is a really high V, and then this V is 0. So we know that there is a potential difference. And as I bring this close, what you learned about was dielectric breakdown. So as I bring it close enough, we'll get a spark that shoots off, but then it's over. It's very quick, very fast, but it's loud, it lets off light, there's some heat involved, but it's gone. And what we want to be able to do is be able to capture this type of thing. We want to be able to use this. It's energy. If we can store up energy, we want a way that we can utilize it to power devices or do whatever we want. Likewise, here's a ball on a hill, so we know up here it has some gravitational potential energy. And if we release it, that gravitational potential energy becomes kinetic, and it's all good until it gets down here. And when it's sitting down here, it doesn't move. And the reason it doesn't move is because there's no difference in the gravitational potential energy between, say, here and here. So we only get movement when we have a potential difference in the gravitational. Over here we got a jump when the potential difference in the electrical potential difference was not equal to 0. Okay, so we can think about fluids. So going back to fluids and thinking about that, if I had these two containers connected by a pipe at the bottom, and suppose the fluid level was here on one side and here on one side. Well, it's the same concept. Here we have a bunch of it's greater height in the fluid, so we're going to have more pressure, and so. Or you can think about it gravitationally as well. You have a UG here and there's a lower UG here, so you have a potential difference that's not equal to 0. And because of that, the fluid will flow. So down here you get some flow of the fluid across. And this is all well and good until they're at the same height. So once they're at the same height, flow stops. There's no flow. And the reason for that is the potential difference is 0 between the two. And we studied this during fluids. And so the basic idea here, if I was thinking about it in a fluid perspective, let me erase this stuff in the center. If I could connect, say, a pump. So if I had a pump connected that was attached here and could move fluid from here and pump it back into this side. So as this rose up, the pump would catch it and put it back over here, and then we could start getting a continuous kind of flow. It's kind of, I think, another analogy that I like is a water slide. So if you think of the water on a water slide, as the water comes down the hill, it falls into a grate and falls into a tube that then is connected to a pump, and the pump pushes it back up the hill, and then the water can come back down, and then we get this cycle, or a water fountain, or not like a drinking water fountain, those fountains that spray water in the air. Same concept. You have a pump underneath, pumps it back up, gives it more potential, and then it'll come back down. So this is the basic idea. And so we can do this with electricity, and we do it with a battery. So the idea is I want to create inside of a battery, we need to create a potential difference. So I need we'll say a positive potential on one side, and then we could do 0 or negative potential on the other side. The point is there's a potential difference here across the battery. And so we do this with chemicals. So inside of batteries, most of our batteries, they use some kind of chemical process. And what it's doing is it's taking an atom and we can knock off an electron. So we ionize the atom. We pull off an electron, and then the electrons will get moved over to one side, like so. So we end up with a net negative charge on one side and a net positive charge on the other, which corresponds to a potential difference across the battery. You don't need to know how it works inside of the battery, but that's the general gist. Now, once these electrons are here, the electrons, remember, are opposite. So electrons flow uphill. They go from a negative potential to a positive potential. And so once these electrons are free, they'll enter into a conducting, this is a conductor, so a piece of wire that connects it. And so what they'll do is they'll start moving through here. And they bounce around. They bang up against the atoms inside of the material. And when they bang against them, that makes them move. It gives them more thermal energy, so you can feel it actually heat up as the particles that make up the wire. So anyway, your electrons will come around because they flow to a higher potential. Then they re-enter the battery and the process starts over. You have this battery does some work on it and pulls it out. The work in this thing is called EMF. We use an epsilon, but we really don't talk about that in AP for some reason. But the EMF is the work that a battery does to move the electrons over. So when we have a battery that's able to separate a charge and create a potential difference, we get a flow of electrons that move around. And these things, they don't move freely, they bounce around. But the movement of these electrons is called electron drift. Electron drift. And this is what we refer to as current. When the current all goes in the same direction, so the same direction, that's called direct current. Same direction. That's direct current or DC current. Alternating current, which we don't study, but is what is in your house, is just that. It alternates. It goes back and forth. And it goes back and forth at a frequency of 60 per second. So 60 times per second, it flips direction. It goes back and forth. Okay, now here's what's confusing. Electrons flow this way, but when we started studying current, I say we as in 200 years ago, they thought that it was positive charges moving. And so they defined current to move from the positive side over to the negative. And so traditionally, we say that current would move this way around it. And so we've just kept that because it was already in place. So when we do current and we talk about the direction of current, we talk conventional current. So conventional current, we think about positive charges moving, although in fact, in reality, it's electrons that are moving, the negative charges. Okay, so now that we have a battery that can act like a pump, moving current around a wire, we can now capture some of that energy that's stored in it, some of that potential. And we do it with like this. This is like an old light bulb hooked up to a wire. And so when we do that, what it does, we'll learn, is we build resistance right there. And so they bunch up and they heat up this little piece of wire, and that gives off photons or light. The bad thing about these types of lights, though, is they also give off a lot of heat. So we get some light from it, but we get a huge amount of heat that comes off of it as well. If you ever touched an incandescent, you know how hot they get very rapidly. So we lose a lot of the potential. And so we have better lights now. We use LEDs and compact fluorescents, those little curly ones. But this is the basic idea, because now we can capture that energy and make it do something useful. Okay, so let's define exactly what current is. And it's similar to flow rate for fluids, and we're just looking at the flow of charge through a wire. And so to do that, what we could do is we could just break up a little piece, and we're just looking for this volume, how much charge moves through here in a given amount of time. So we care about time. So we'll define current to be like for this little piece of wire, what's the change in the charge, the big Q. So the number of charges that pass through, that builds up the entire charge over time. And that's current. The units on this thing, charge is coulombs, and that would be seconds, and we call them amps. And we use just big A. It's after Ampere, physicist. Okay, so let's see an example. So if we wanted to determine the current in a wire in which 1 times 10 to the 7th electrons are passing through every second, then we just use the definition. The current would be the change in charge over the change in time. The charge would be the charge on an electron, we'll say Q, times the number of electrons divided by delta T. So we get the charge 1.0 times 10 to the, I'm sorry, that's the number, that's the N, times the charge on an electron, which is 1.6 times 10 to the negative 19 divided by 1 second. And we do that, we get 1.6 times 10 to the negative 2 amps. And that's that would be 0, what, no, wait, 1. If we go over 1, that would be 16 milliamps. And 1, 2. If we go 1 more, that's 10 to the negative 3, which is a milliamp. So not much current. So a whole bunch of electrons, not a bunch of current. Anyway, this is the definition. It's on your equation sheet. Just know it's amps. All right. So now we can start drawing circuits before we talk about them. So these are the symbols that we'll use. So for a battery, we draw it with, this is a single cell battery. You'll see, if you look online and you start watching, you'll see where they have like multiple cell batteries. Something like this. It's like a 2-cell battery. Anyway, we'll just use these. So you have a positive side and a negative side. So the long side is the positive side, and sometimes you'll have the potential at that side written out. We typically will set the negative side to 0, and then the positive side would be whatever the potential difference is across the battery. Wires are just lines. A bulb is this little thing, so I usually draw like an E, and then just draw a circle around it. And that would be a light bulb, any kind of light bulb. And then we have resistors. We'll talk about these. These are just resist the flow of current. So they're just little jagged lines. A switch. So this is an open switch. And this is when it's closed. A capacitor. So you make sure that the plates are the same. This is a parallel plate capacitor. It's different from a battery. And then we have 2 devices that measure things. We have an ammeter, which measures the current. And we just put an A in a circle, and a voltmeter, which measures your potential. I'll talk about how to connect these things and how to use them. We'll be doing this in class. So how could we draw a simple circuit? So I guess our simplest would be a battery connected to a light bulb. So you just draw your battery, positive, negative, maybe 9 volts, and then it comes across a wire, and then it's connected to a light bulb. And then it comes back, goes here, put a circle around this. There you go. There's your simple circuit, a battery connected to a light bulb. Which way does the current flow? So we would say that I goes this way. That's your current, moves around like this and then comes back around. Which way do the electrons flow? Well, electrons go this way. All right. We could have more complex circuits. So you could have, say, a positive, negative. We could connect it, we could have a resistor, then we could branch off, have a capacitor connected to a light bulb, and then we could branch off up here, put another resistor, another light bulb, stuff like this. We can make them as complicated as we need. But that's the basic idea. You'll get used to drawing these. Let's talk ammeters and voltmeters. So here, if I wanted to measure the current, so if I want to know the current in this wire, I'd have to connect the way it's important how you connect these things. Let me erase some of this line. So an ammeter has to be connected, we say, in series. So it would have to be here. In other words, the current has to come in, go through the ammeter, and out the other side. So it always has to be in a line, and it will tell you the current through it. A voltmeter, on the other hand, is connected like this. So it has its own little branch. This is called parallel, because what it does is it measures the potential here, 1, and it measures the potential here, 2, and then it subtracts them. No current actually goes through this. It's just measuring the potential at these 2 points, and that will tell you the potential difference. But that's basically it for this lesson. So we talked about current, how we can make it using a battery, kind of what goes on inside of a battery, and then went over basic circuit diagrams.